Probability can be applied to figuring out the chances of winning various lottery games, and I'm going to show you how that works. So here I have 18 people, 8 of them are boys, 10 are girls, and I picked 4 people at random. So there are 18C4 things that can happen, which is 3,060. But I want to know, some of them have 2 boys and 2 girls. Well, that becomes one of these boy-girl counting problems. I can pick 2 out of 8 boys and 2 out of 10 girls. And I multiply those together, not add them, because each pair of boys can go together with each pair of girls, so in that way they get multiplied, and we get 1260. And that ends up being about 41% chance. So this kind of thing that has this structure where it's something sees something times something sees something over something sees something, where the 18 is the sum of 8 and 10, and the 4 is the sum of 2 plus 2, that's going to happen in the New York Lotto game. The way New York Lotto works is that there are numbers from 1 to 59, and you pick 6 of them. Maybe you say 10, 12, 41. The order doesn't matter, so it doesn't have to be 1, 2, 3, 4, 5. Then they pick 6 numbers out of 59. They have these ping pong balls, and you win first prize if you get all 6, and second prize if you get 5 out of 6, and third prize if you get 4 out of 6. I want to show you how to calculate out those different probabilities. For first prize, there's only one winning combination. So we can say 1 out of, now the total number of tickets you could buy is 15C6, which is actually about 44 million. So assuming this game costs $1 to play, it's 1 out of 44 million chance of winning this game. Only one winning ticket, these numbers. Gets a little interesting when we get to second prize. There are still 59C6, 44 million different tickets you can buy. But now, let's say the numbers that came up just were 1, 2, 3, 4, 5, 6. So who would win that game? Well, someone with 1, 2, 3, 4, 5, or 1, 2, 3, 4, 6, or 1, 2, 4, 5, 6. There's sort of 6 sort of ways to win. But for each of those ways, there's also a wrong number. Like they could have 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 8. 1, 2, 3, 4, 5, 9. This actually turned out to be a boy-girl question. We're picking a 6-number sort of committee, but we want to pick out of the 6 winning numbers, we want to pick 5 of them. But if you don't have this other part, there's also, we need to pick 1 out of the 53 numbers that didn't come up. If you leave off this thing, you get the wrong answer by a pretty big factor. This reduces to 1 in about 140,000. Again, without this, you'd be saying that there's only 6 winning ways to win, but there aren't, because for each of those 6 ways, there's 53 wrong numbers. Again, 1, 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 8, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 9. I can go all the way up to 1, 2, 3, 4, 5, 59, and then I start with 1, 2, 3, 4, 6, 7, 1, 2, 3, 4, 6, 8, and so on. So there's actually a lot of numbers up here. Well, it's not that many, it's about 300. This equals about 300. So there's a 300 winning second place possible, different winning place tickets. And for third prize, we do a similar thing. 59C6 is in the denominator, but here we want to pick 4, like 1, 2, 3, 4. But then I also have to pick 2 of the bad numbers, like I could have 1, 2, 3, 4, 7, 8, 1, 2, 3, 4, 7, 9. So there's actually a lot, and it ends up being about 1 in 2,000 chance of winning that game. So that's lottery games. Here's an interesting lottery game. someone gives you 2 dice and they give you 24 chances to roll double sixes. And if you can roll double sixes before you get to within the first 24, the game stops and you win. And if you, after 24 rolls, you still haven't gotten double sixes, you lose. One argument is that this game is a good game because it seems like there's 36 things that can happen, 36 possible outcomes when you roll 2 dice. So you have a 1 in 36 chance each time of getting double sixes. So it feels like 18 chances, 18 out of 36 is 50%. So anything more than 18 seems like it's good for the person who's playing. But it turns out this game is actually not good for the player. And it's actually somewhat of a Bernoulli experiment. It's imagine I kept playing after I won. It would be the probability of getting at least 1 double sixes in 24 chances. Easiest way to calculate that is to do it indirectly. 1 minus the probability of getting no double sixes in 24 chances. Well, not getting double sixes 24 times in a row is 35 over 36 to the 24th power. And this ends up being about 49.5%, which is slightly less than 50%. So it's actually not a good game, or it's close to being a good game. This idea of indirect probability works into the very famous birthday problem. The way the birthday problem works is, let's say there are 24 people in a room. What's the probability that 2 of them have the same birthday? Like maybe not the same year, but the same day. And let's ignore leap year for this. Seems like it's a pretty low chance that 2 people have the same birthday. So if there's 1 person in a room, the percent chance of no 2 people having the same birthday is 100% because there's only 1 person. And if we subtract that from 1, we get a 0% chance that there's 2 people with the same birthday, of course. But when a second person walks in, the chance that that person has a different birthday from the first person is 364 over 365, which is practically 100%. And so the chance that there's at least 1 match is 1 minus that, which is still pretty close to no chance. When a third person comes in, for them all to be different, 2 things have to happen. The second person has to be different from the first person, and the third person has to be different from both the first and the second. That only leaves them 363 days to be born on. And that's still practically 100%. 364 over 365 times 363 over 365, which is still a practically 0%. But if I keep going with this pattern, when I get to, I think it's actually, can change this to 23. When I get to 23, it's going to have something like this. On the bottom is going to be 365. When it's 3, there were 2 of them. So when it's 23, there are 22 of them. And on the top, I'm going to have 364, 363, all the way down. When it's 3, is 365 minus 363, 365 minus 3 plus 1. So this is going to be 365 minus 23 plus 1. 365 minus 23 is 42 plus 1. So it's going to go down to 343. That's the chance that no 2 people have the same birthday. When I subtract that from 1, we can actually write this as 364 P22. It ends up being about 50%. So there's a 50% chance, and if there's like 30 people, it goes up to like 35 people, it goes up to 75% chance. Okay, so those are some gambling games and this birthday riddle that can be analyzed with probability.